So we are setting up for our next speaker on Julia-powered BI engine.
Is this yours? Oh.
By Matthew.
Yeah. Let's see if it'll work. Yeah, then let's make sure I got enough power. Okay, so I'll you run.
The floor is yours.
Okay, well, hello, and thank you guys for letting me be here. I see we got all the cool kids in the room, so that's pretty good. So I'm Matt Muyres. I work with a group called Planview, and we've been working on building a BI engine in Julia, and the goal is to basically be able to get away from the current technology that we have and move off into something that's more cloud-based or more distributable. And so what I wanted to show you today is what we built and kind of where we're going with this. So in this presentation, I wanted to kind of delve into some of the aspects that we have here, what we've done, and I kind of give you a little bit of the target audience for people that might be actually interested in this. Some of the key takeaways that we're going to try to shoot for here is try to understand the benefits of the framework and how we do this manipulation and analysis in Julia. This new technology that we brought up that I refer to as chained formulas, how we do the caching and the programming and how oxygen plays into that. And then we're going to try to show off some of the insights that we've gained and the challenges that we've run into during this project, which has been roughly 2 years in the making. And then we'll talk a little bit about how this is actually making the Planview Advisor product better. And then so quickly, I just kind of want to show you guys what we're doing here. So this is kind of what we're trying to generate, right? So this is what the Planview product generates. It's a simulation type software for BI, portfolio analysis. We primarily focus on, life science, pharma, medical devices, but we also do things like oil and gas and stuff like that. So it's not specific to any particular vertical. It's really based on the skill set of your modelers determine the capability of the application. And so here's an example of some of the graphs and stuff that we make, the example like simulation, a lot of people see this. And we do this in a way that allows this types of simulations to be flexible, so you can change the type of simulation or the bounds and a lot of things like that. But that's not really the main point of the talk, but I just wanted to show you some of this. This is kind of the big picture of kind of what we do and kind of what we're doing with Julia. Okay, so you can see here a lot of stuff on this slide, a lot of eye candy here. There's a lot of areas that we deal with, and I want to just say types of different simulations. You can see we do Monte Carlo, we do the median, Latin, hypercube. So there's a lot of things that our customers want. And so what we're doing is we're trying to move into a world where we can just make it run faster, right? Faster and better, and scale it and deploy it. And so this is kind of our physical architecture of what the Advisor product looks like. And you can see over here that we do have the Julia piece kind of in spot here. So this is where JuliaHub comes in, right? So we have this big architecture with all this stuff. And then it's like, oh, by the way, let's bolt on Julia and see if we can make this thing run better. And so the project here, the JADE project is what we call it. It's basically we're trying to create a high-performance engine. This is developed primarily in C#. The actual JuliaEngine is in C#. And then the JADE piece is actually pure Julia. Okay, and so the JuliaEngine is really a math formula translator. It reads, I'm not gonna say all of them, definitely not, but it reads several third-party languages and some standard shorthand languages that are out there, and I'll show you some of that. And so the deal here is that we have the C# engine that manages all the formulas, controls some internal caches. It's the gateway or overarching piece for the entire, I want to say transformation engine or decision engine. JADE, which we're just lovingly calling, just another decision engine, right? No big deal, right? But this is actually a bunch of modules, not a lot, maybe less than a dozen, and it's used to actually drive all the formula chains. So we create all these chains and all these variables and push them into a model that is built programmatically, right? And so we go from a representative model into a programming model, and then that is loaded up into Julia. And some of the core pieces of our framework, we have this notion of it's basically like these 4 pieces. There we have an NDTable or an n-dimensional table, which is really multi-dimensional arrays that have intelligent indexes. So instead of just being a standard matrix, you have a matrix where every dimension of that matrix has a well-defined index that's bound to it. And we use that to allow ourselves to better flip and spin and slice and subset the matrix. And then we have things that are known as like an index. Kind of makes sense, a discrete value of ranges. We have this notion of a choice, which is like a list of things you can choose. And then, of course, we have the smallest thing, which is a scalar. And the idea here is that we break everything down to a set of these 4 objects. And then from these 4 objects, you can do any kind of math that you want. So that means you can take like an NDTable and add a scalar. And when you do like add or multiply, it knows what you're talking about, right? It knows that means that you're going to add that scalar value across the entire matrix. Okay, now if you said, well, I have something like an index. Well, can I add indexes together? Of course. Can I multiply them? Of course. But could I add an index to a table? And what does that mean to multiply an index to a table? So we worked this out into a structural language that allows you to then do fairly simple formulas that do very dramatic data manipulation. And so this is kind of an example of some of the structures. As you can see, it's pretty simple, right? I mean, as far as for tracking and what you really have in here, we try to keep it as simple as possible from a structural point of view. You can see all these are mutatable, so that we do things like where we inline mutate structures that are the result of a formula. And so the framework is basically set up where we have dictionaries of formulas and dictionaries of structures, and the formulas produce structures, and the structures are habitually used for doing your actual math calculations or the formula calculations. And then this is what the Julia engine looks like. We can see here we start with a BI model, a business intelligence model, that basically is the representation of all the math and the formulas and the outputs that you want to generate. It contains things like tables that would be static that a user might manipulate or enter or change. And it also contains, simulation or stochastical formulas for generating any kind of output that a client would want. Okay, so this basically comes through and is turned into a bunch of chains that are then fed into this model manager. And all this is written in C that you pretty much see. This is all written in C#. Okay, so in this model manager, basically reads these text files in, and you can write it in a number of ways. It could be like an INI file. You could write it as straight text files. It could be MATLAB type formulas or Python formulas and stuff like that. And so, and different people use different interfaces to do it. You can use a UML type interface. It generates a text file. It could be a spreadsheet that generated all the formulas. It really wouldn't matter. Okay, so then this basically brings them all in, and we have something that we consider as what's called a block parser. And the block parser will take the discrete chunks that describe what the formula is, things like the name, give you a name, a title, some information, and then the actual formula definition itself. And that formula definition can contain anything from standard math formulas to things like references to the other variables. So you can have, variable A plus variable B, right? And in this case, it might be something like all regions is reduced down to a matrix of data that has trials or samples or medical information. Okay, so this model is actually a bona fide object. So it basically comes into existence from reading from this block parser. And then it generates a formula graph or a graph model of all the formulas and their associations, right? So it creates a full hierarchy of upstream and downstream associations and binds everybody together so we can understand what might change and what needs to be recalculated. Okay? And then from here, this model manager actually turns it into a model graph, okay, which is a little different than the formula graph. So the model graph is a bigger, more robust representation of all of the business logic. Okay, and so from here, we now have everything that we need in order to start processing. Okay, so all this is fed into the JuliaEngine. Once again, this is also C#. And this JuliaEngine then has a lexer and a parser. Now this is actually external. Okay, so this is some of the magic that I wrote here. So this lexer will create a lexicon of the language or the formulas that you're looking at. And then the parser will translate that lexicon into Julia. Okay, so then the idea here is that if you want to support other languages, you only have to adjust the left-hand side, right? You can make a different lexer, or you can make the lexer smarter, and then the parser will understand how to create all the Julia code that you need. And the code that it creates is specific to the Planview functions library that we've generated, and I'll kind of show you what that means. So then this lexer reads in the formulas from a third party, generates the JL code, and then that then comes out and we feed it into a cache. So the idea here is we don't want to redo the work over and over. So every piece of work that we do, we end up saving it off to the side. So we're using a manufacturing approach to building the actual BI system. So as all these pieces flow through, they get chunked together into smaller components and then larger components to where we can do basically a just-in-time engine creation. Okay, and so from here, this engine will then take all these subcomponents that it's built, and then it will actually run it out and create what is known as the engine data. Now, engine data is basically the thousands of formulas all put together into a Julia language structure that primarily consist of nested functions, functions that define data, functions that define the object. And then this separation allows the functions to be reinterpreted at real time when the underlying components change. And then this JADE engine has its own internal state cache. And this allows us to store the current state of the engine so that we can come back and reset to a point in time. Now, this is useful for what you hear a lot of people talk about is this precompile problem and this just-in-time problem. So what we're trying to do is we're trying to get away from all that. So this way we can pre-train the engine and then also post-train the engine so that when it's running, it'll get follow-on training that is the real-world math that it needs to do. And then by doing that, we can save it all into a state and restore that state. And then we get about 10 times the performance of our initial run. And then by doing this, we can create these engines in the background, set them up, get them going, and then we have a really fast turn on it. And the state in between these two, there's a process state that is linked in between these two so that the engine knows what the story is of the JADE computation piece. And then oxygen is used up here is the main interface. So we have an internal linkage, there's like a process level linkage, and then we have this external linkage. And the external linkage is basically API calls, REST calls. And so this engine is actually freestanding. Once it's up and running, it really doesn't need necessarily the rest of the architecture. Like you can connect to it through another API setup. You can use a web interface and, and in theory, you could make and create and do stuff. You could even do it through like curl commands or something like that, because I don't even need to go down this path. Okay. But if the engine goes, you've made something dirty, you've changed some data, you've changed the table, the user has adjusted something, and I don't think I have the right stuff. So I'll communicate over to here, tell this engine to do the work that I needed to do, pull the data back over, and then I'll store it again. And then I also will communicate back through Oxygen any kind of hierarchical or dependency changes that the engine believes happened that JADE doesn't know about. Okay, so JADE is savvy enough to figure out a significant amount of the hierarchy and maintain upstream, downstream relationships, but not necessarily if there's some kind of low level or complex change that the engine does, because a lot of this can happen dynamically. We have something that the engine does is called node farming, where it will generate thousands of variables on top of the thousands of variables that are already in here. So the system will come up with a default set of data or a default set of formulas. And then based on the processing and what we need to do, we'll create more of these variable farms or node farms to do follow-on processing based on what the user is attempting to do. So that could be things like complex waterfall, tornadoes, unwinds. We might need to make more stuff. And so we'll make it on the fly and then synchronize between these two. And then, of course, if there's a change in the graph state because of the model changing, then we have a link here where the graph state is maintained between these two objects. Okay. And so that's kind of a lot. Okay, so, and then kind of getting into what the engine is. So the engine is basically designed to, this JuliaEngine is designed as a code generator, right? And so it will produce the code that creates the JADE piece. And then JADE is designed to run both locally or on Hub. So you have a manufacturing process that creates all the libraries, it creates all the function routines, it generates all the code, and then it precompiles it, it exercises it, and then it stores it. And then from there, we're able to create both local packages or sys images on JuliaHub in order to control how we really want to use the capabilities, right? And so here we talked a little bit about there's this manufacturing approach where you build once and assemble many, and this allows us to then bring systems up or the different components up very fast. We have this notion of state capture that I kind of talked about on the state piece, and that allows us to store the state of the current engine so that we can then reset it. And the resetability is one of the key technologies that we have here because it allows you to keep a fully precompiled hot instance of Julia that is ready to go. And this will, like, it increases performance either 1 or 2 orders of magnitude from a kind of a dry run where you have to have intermediate compilation. We support a hybrid approach where you can run this locally and remote at the same time. So the Advisor product runs a certain set of operations locally for expediency and latency control. And then the background processes that run for background data set recompilation, data ingestion, and things like that, data imports that require an engine to recalculate data or to normalize data, then it'll run in the background, and those background processes will be fired up on Hub. And then this allows us to scale large data loads out onto Hub and then have fast responsive engines for user interactions. So when there's a user behind the process, we want it to just be as fast as possible. And so, and if the user isn't there, we kind of don't really care. It can take a little bit longer and you can put it in the background. One of the big differences with this setup is that we are a high frequency interaction, high frequency change system. So maybe a lot of the Julia things that are done are more the fire it off and go to lunch and come back and get your simulation results. In our world, the users don't want to wait on that. They don't want to do any of that. They want everything to be as fast as possible. So they don't care if it's a week's worth of work. They still want it within a few seconds or a minute, right? And so that's kind of one of our big things here is the frequency change. We do support several third-party languages. The Lexer is designed to read both formulaic and shorthand, and it produces Julia code. The parser then produces the Julia code. And I'll show a few examples of that. Locally, we use compiled modules, right, where we build a module, and then we pre-compile it and store it as a package, and then reference it at a package level. On the Hub, then obviously we make system images, and we manage those. And we found out that, yes, if you have your manifest with specific libraries and stuff that you're using, and you have your code, the system image will include your code. Okay, now, maybe that's not something that everybody understands or believes, but it is an important thing. Okay, so that means you cannot have one manifest and multiple code bases at the same time, where I have my function library, and then I have a set of libraries I depend on that's in the manifest. If I change my code, that system image needs to be updated because that code will be in that system image. Okay. So what we do is we have changed things to where that engine data that I talked about, that might be 25,000 or 50,000 lines, it's not part of the system image. It's held as a side piece that's included real time. And then this lets us do training on all the functions and routines that go into the system image for the performance gain, but avoids pollution of the system image with the engine data that may be from different models. Okay, so the Advisor product tends to have multiple models that run at the same time, and those models interact with each other. And so because of that, we pull the model data out and leave it on the side. And then we dynamically load it at runtime once the image comes up. And we do a lot of workload training to improve performance. We do both pre-training at the precompile time, and then we also do runtime training when the system is actually up and going. Some of the benefits that we've run into, some of our benefits and challenges here. It is a very flexible framework for sure. It supports a lot of extendable features. You can just keep kind of adding on to it, whatever you want. Somebody comes up with something new, they can just kind of plug it into the library, and then you can just start using it, just using it. The chain formulas, they smartly recalculate. It has this whole hierarchy tree and everyone knows their dependency. And so therefore everybody knows who's dirty and who's clean. And then we only recalculate the dirty nodes or the dirty variables. And then that allows for lightning fast calculations. And then because as you go farther down the calculation stream, it becomes more complex. And that endpoint tends to be what the user wants, which might be a summary, a graph, some kind of data. Okay, and like we said, we support the high-speed changes and high-speed recalculations, and it supports dynamic workflow. Okay, so this is where I was talking about you can dynamically alter the model real time based on programmatic needs. And so therefore, if you want to do a set of calculations that require formulas that are not in existence, you can have the system dynamically create all those formulas and create all those associations, and the system will naturally understand where those fit in the overarching hierarchy. And then they will smartly participate and recalculate. Some of the challenges that we ran into is obviously third-party languages. Creating a lexer that will take apart a third-party language and create a lexicon that you can then run through a parser is fairly difficult. And so I'm the one that wrote that, and I will attest to the fact that it is fairly hard. Even with AI support, AI kind of sends you astray sometimes on those. And then one of the big things was learning what makes Julia happy, right? I mean, I think we all might struggle with that, right? What is it that makes the language happy and performant for you? So that was a little bit of a learning curve, and we definitely thank the JuliaHub guys in advance on that one here. They have helped a lot for us figuring this out. So we didn't have to do this. We didn't have to do all of this on our own. We actually had some help ramping us up. Debugging, I think a lot of people know that debugging a running process can be difficult. Some of these engines will have 1,500 variables. Some of them will have 4,500 variables or 4,500 formulas that are all chained together. And our system is eventually consistent, so it's also self-healing. And so that means that as it runs, even if it had an error, it might self-correct that error and then keep going. But that's not always the best thing because it's hard to figure out what the bug or the problem was or the crash point because it didn't stop the system. The system doesn't just stop and crash because there was an error or a problem. It keeps going, whether you like it or not. And so we wrote a way to record and replay all the activities of the engine. And so this lets us then run a set of scenarios, and then if we run into a problem or a bug, we can record the situation, you can pull it off onto the side, you can give it to your other team, they can run a replay that back to the crash point, and then they can look and go, oh, I can see exactly what went wrong, I made a mistake, or I didn't understand something, or I have a signature that's wrong. The other big thing was package creation, right? How do you do all these packages and how do you create them and manage them when you're doing all this programmatically? All these are being created on the fly. And if you want to stack these on a server, how do you keep them from conflicting with each other? And how do you keep yourself from basically breaking another running instance if you have common packages that are running on the server. And so this was a lot of the big things that we had to address. So let's see. And so here I want to show off a couple code examples. This is one that my cohort Chase wrote. And so this is basically what we call a remap. And so we deal with a lot of flat data. And so we have this notion of flat files and flat data, right? Which is very much like a sparse array, right? So the deal is, do you really want to unwind all these to look at them? Let's say you have flattened data, but it's a matrix that might be 5 dimensions, but it's been flattened down. And then you only have the data that's changed in this flattened dictionary or this flattened set. And typically you blow it up or you unwind it, right, into the full set or the full matrix before you typically operate on it, right? Because if you have a flat data set, it's really hard to do matrix operations because it's not a matrix, right? It's totally not a matrix yet. But if you unwind it or inflate it, then it becomes a matrix. So what we've done is we've created this remap notion where you can remap the locations of a matrix down to its flattened components without unwinding the whole thing, and therefore you avoid creating intermediate matrices that may be like hundreds of millions of cells, when really there might be only hundreds of thousands of pieces of data. And so this allows us to then do this. This is like our unflattened loop. This is chunks of code buried inside of chunks of code, right? But this is an example of where we would be remapping a coordinates that was coming in as we were unflattening the data. And so this lets us go through and do operations without fully inflating the data. This is an example of some formula transformations, right? You can see some of this is pretty simple, right? We support basic structured languages, and you could say, well, Matt, that doesn't even really need to be translated, right? I mean, Julia will probably do that, right? But that's not necessarily always true, because the people that write this stuff, they don't know Julia, they don't follow syntax, they just know some basic formula creation methodologies, and then they know things like this shorthand, okay? So here you can see where one of the things we ran into is scope, right? When you do this, there is scoping issues. And so if you don't localize a lot of these things, you'll get scope bleed, and then your functions will be all over the place. This is an example of shorthand. Maybe some people recognize this from Python and MATLAB or some other things. But this is an example where the parser will take this apart, or the lexer takes this apart, and then the parser will produce this. And we can see this is our NDTable here. And then we can see that this is basically the formula that would be generated. As a very small example, this would be like one formula that would be generated. Here's another example of a variable, like this is our bi-quarters year type formula, and we can see that this uses something that's called a vectorizer that basically has the ability to read through arrays of formulas and know the difference between arrays of formulas, or arrays that might have dimensional data in it, and then it can inflate the top level table. So let's say you have a one-dimensional table, but every entry in that table is 2 dimensions. The vectorizer goes, oh, I understand what you mean. Let me turn that into a 2D table, and I'll bring the indexes from the lower level up to the higher level, and we'll normalize the whole thing back out. And so this is an example of what it makes in order to make like one simple variable. And then here is an example of something very similar, only this one is like a choice. And so here we can see where we have this notion of the data piece that's being created, the actual index piece that's being created, and then we have this notion here as we run, are we going to dynamically build this or not? If it's already built, then we'll skip it. And then this is considered a piece of static data. And static data can be externalized so that we can fast load it into the system, so you don't have to go back through the formula building process. And then this is an example of a larger formula, right? This is a more robust example of a fairly reasonable size formula. And so you could have thousands of these that chain together. And the main way they chain together is this little guy right here, this get var. As you notice, we do this thinking like get a variable is what that really means. And then the variable has a name. And then this one will have a formula in it. This represents either a formula or a structure. And then based on where the computation, the calculation happened, these are either already calculated or not. And we can see that these take standard structures, name structures, right? And then we basically created an overload map that overloads all the Julia operands. So we basically have overloaded all the operands so that they understand how to work with our native syntax and our functions. And then this is kind of some of our stats here. So you can see some of the modules that we used, and then some of the code lines that we've generated. We can see that we generate about 20 to 50,000 lines of code. The actual routines that we built for Planview functions runs about 10,000 lines, about 1,000 lines in Oxygen, and the engine is about 5,000 lines. So you can see it's not that big until you get down to the code generation piece. And then kind of with that, I will definitely say thank you to my coworkers, Ohad and Chase, and thank you to the JuliaHub guys, Phil, Matt, and Luke. And I think with that, are we out of time? Yeah, okay. I can take.
Thank you so much, Matt. I think I'll take one question because then we'll go to our last talk of the session. One question.
So just curious with the Jade engine. So some of these formulae that you displayed there, do they have to? I mean, can they change dynamically over
Yes.
time as well? Okay.
Yes, absolutely. Absolutely. And so as this runs, I'll just show you. This is an example of the engine running formulas. So this is the output that is generated when we run and calculate things. And just as a quick thing, I know we're out of time, but you can see the graph comes up, right? And you can see this is a running engine. We change to another piece. You can actually see the engine recalculate different formulas. And if we go to something a little bit deeper, under the analysis, maybe a tornado, you can see all the formulas chain recalculating there on the screen. And so as it does that, it goes faster. And so as the system runs, these formulas may change on the fly. And so that's why we maintain the hierarchy and the dirtiness factor. So we only recalculate formulas that have actually changed or have a impact on them.
Okay. Thank you so much
Thank
for
you.
the awesome talk.